Okay, so where are we? We're talking about classification problems and supervised learning. We talked about rules. We talked about decision trees. And then we said a challenge of decision trees is that they are prone to overfitting. And so there's methods for avoiding overfitting in individual decision trees that we didn't really talk about, such as you build them and then you can prune out parts of the tree and aggregate parts of the tree so that they become a little more general. But instead we shifted to another more general and more powerful technique to avoiding overfitting, which is to use ensembles of models. And so within the context of ensembles, we talked about boosting, and in particular, mentioned this algorithm AdaBoost, which is a meta algorithm, meaning that it works on any machine learning application. It doesn't have to be about trees, but we talked about it in the context of trees. Then we talked about bagging, which is about selecting subsets of your data to work on. And bagging itself relies on the bootstrap, which is a technique for resampling the same data set in order to derive estimates of important statistics. Okay, and we put some of that together and talked about random forest, which is an ensemble method for decision trees that has a couple of unique characteristics. Now, I went through this rules and then decision trees and then ensembles approach, sort of sidestepping postponing the regression-oriented machine learning models. And there's a couple reasons for this. One is random forests do turn out to be a pretty powerful method, a pretty general technique for a lot of things. And generality, not just in their statistical power and their sort of efficacy in practice, but also the fact that they work on categorical attributes, the fact that they can handle many attributes, so big P, smaller n cases, the fact that they can, there's different variations of them that you can experiment with, the fact that frankly they're kind of simple to interpret the results of, and also maybe even simple to implement yourself. You know, hopefully you're armed with enough knowledge where you think you could make a go at this. So I think they're actually a pretty fantastic general purpose approach. All right, so let's consider a different method that's not rule or tree based. All right, so that's nearest neighbor classification. So here, this is actually one of the simpler ones, and there's a reason, you know, it'd be reasonable to actually present this first, but the reason I didn't do that is that it assumes only numeric attributes, and I think a lot of the intuitive data sets you work with, especially when you're coming from kind of a you know, maybe data processing background, data science sort of scenario, as opposed to a pure machine learning, pure statistical you know, background, the categorical data is quite common, and so defining nearest neighbor is sometimes possible, but it's not always very natural. Okay, but now that we've sort of covered the more general techniques that can handle categorical data, we can think about these. So nearest neighbor is dead simple, right? This is to say, plot your points in a space like this, where the red squares represent one class and the blue squares represent another. You know, maybe survived or not survived in the Titanic example. And when you have a new point that you want to classify, just drop it into the space at wherever point it, you know, the attributes tell you where it should go, and choose the class of the nearest point to it. Okay. So what's the class of this green triangle? Well, the closest point to it is a blue circle, so we call it blue. And what's the closest point to this green triangle? Well, that one's a red square, so we call it red. Now, as you can see in the second case, maybe it's not that reasonable to call it red, because perhaps the class boundary is sort of something like this, and this one's, you know, an outlier. This one's a mistake. And so we perhaps would misclassify this second green triangle. All right. So the intuition here is, you know, going back to this sort of document classification example, well, the last document I saw that mentioned the word Falcons and the word Saints was about sports, so I'm just going to go ahead and assume that this document is also about sports since it has the same terms in it. Okay, and so this is not the most unreasonable method to use, but as we saw, you know, perhaps it's a little bit sensitive to noise in the data. And so another, you know, a simple extension of this is to imagine k nearest neighbors as opposed to just one nearest neighbor, right? So you find the k closest points and then they take a vote on what class it should be. Okay, and this gives you a little more resilience to noise in the data um, at a cost. So you can ask yourself, how would you choose K? All right, what should K be? Well, the benefits of a small K are that it's fast, and there's less of a bias towards popular labels. And what I mean by that is that if you have imbalance in your data, right, so you have, say, many more people that survived than didn't survive, then there's going to be a lot of those blue circles relative to red squares, let's say, right? And so therefore the odds that you're going to land somewhere near a blue circle, assuming a certain amount of noise in the data, goes up. And so you'll start to misclassify more and more and more, as a result. And so imbalance in the data translates into higher error rates. However, the benefit of large K, even though it's sensitive to imbalance, is that it ignores outliers, right? You're insensitive to the outlier. So choosing a K is perhaps problem specific, and there's been work on making this more precise. Okay, so the other decision you need to make is some kind of a similarity function. And so typically you would imagine just Euclidean distance in these cases. But another one that might make sense is cosine similarity, which is a measure of the angle between the two vectors. So if you have 2 points in space, this line D is the distance between them, while the cosine similarity is how far apart they are in the angle. So you have to think a little bit about what the trade-offs are here. So if I was in the classroom, I would ask you guys, I would wait for some answers, but since I'm not, I'll pause dramatically and then just talk about it. So one thing to remember in general is that when anybody asks what is the problem, what is the disadvantage of Euclidean distance, you should always have the same answer in mind, right? There's one big disadvantage of Euclidean distance, and that is that it's sensitive to the number of dimensions. So as the number of dimensions goes up, the distance between points is sort of hard to interpret, right? Because it tends to go up as well for not necessarily any kind of good reason. And remember that a lot of these machine learning applications will have a very large number of dimensions, right? So all the English words, for example, in the document classification case, all right? So that's fine. That's the disadvantage of Euclidean, is that you have this sort of curse of dimensionality problem going on. The disadvantage of cosine is that it kind of favors the dominant components, meaning that if two vectors are the same in all dimensions except for one where that value is much higher on one vector than the other, then the cosine similarity is affected less by that than the Euclidean distance. I should try to draw this real quick. So if I've got a point here and here, and then I've got a red point here and way up here, then the angle to the blue is that, while the angle to the red is that. And so this distance is relatively less sensitive to this increase than Euclidean distance, where this point and this point are much further apart, are sort of linearly far apart. Okay, so what this translates into is that you'll tend to be more similar to neighbors who have a very large value in some dimension. Okay. And that can be a good thing or a bad thing. So in one paper they talk about sort of this being a good thing for image retrieval, because if you have very striking features in terms of, say, color composition of the image. So this is like, you've got a query image and you're trying to look for other similar images, and you extract a bunch of features from the image and you try to find similar ones, and then you want the K nearest neighbors. Then say you have very strong red and brown or red and blue kind of colors in your image, then you're going to find things that have red and blue, but perhaps less extreme. Right. Okay. So lower magnitude, but still red and blue, is should be a return in the results, while close in magnitude, but in a different dimension. So about the same magnitude intensity, but in green and yellow, is perhaps less similar in that application. But this is all very application dependent. Okay, so one final point I want to make about this is this notion of Euclidean distance and its sensitivity to the number of dimensions. So this is random data normally distributed with some variance of, I don't know, 2 or 1 or something like that. I guess a little more than that, probably more like 4 or 5. And just taking 2 points in a d-dimensional space where d is going from 0 to 1,000. So give me a random point in a 500-dimensional space, and give me a random point in a 500-dimensional space, and measure the Euclidean distance. Okay, and so you can see the Euclidean distance is sort of going up with respect to the number of dimensions, even though the random distribution from which these points are drawn is the same. And so as the space sort of expands exponentially, things get sort of further and further apart. Okay, and so this may or may not be the effect you want when you're trying to measure similarity in a high dimensional space. All right.